Hi, my name is Patrick Grady, and I'll be presenting on our paper, PressureVision++. First, we begin by reviewing the prior work, which our project is based on. The original PressureVision paper took an RGB image of the hand as input, and output a pressure image showing the location and magnitude of pressure. They rely on the fact that as a hand presses against an object, it changes in subtle but predictable ways. For example, in this image, as force increases, the shadows cast by the hand change, the distal joint hyperextends, the skin underneath the fingernail loses color, and the tissue deforms. PressureVision showed that these subtle visual cues can be reliably interpreted to estimate pressure. In order to train their network, they capture data with RGB cameras as participants interact with a high-resolution pressure sensor. Their network can accurately estimate hand pressure. However, their model does not generalize past the simple, untextured surfaces it was trained on. Our work, PressureVision++, seeks to generalize more broadly. To improve generalization, we must collect more diverse training data. However, this presents challenges. Imagine we want to capture pressure data as a person grasps a mug. Prior work used flat pressure sensors, which cannot conform to this shape. However, a variety of flexible pressure sensors are available, which can be wrapped around curved objects. For example, they can be wrapped around a can to measure pressure as it is grasped. However, since our methods use RGB images, we want the appearance of the object with sensors to be similar to the appearance of the real-world object. However, sensorizing the object changes its appearance, making it difficult to gather visually diverse data. Building on this, imagine that we want to observe the hand as it opens the can. Our pressure sensors cannot conform to the complex ridges at the top. Generally, real-world objects have complex geometry or may be soft, exceeding the capabilities of currently available sensors. We find that instrumenting diverse objects with pressure sensors quickly becomes impractical. We develop a novel way to circumvent this issue. First, we collect a limited amount of data with the pressure sensor, similar to prior work. We also collect a large amount of data without any pressure sensors. We prompt the participant to make contact with the object and then start recording data. Since we know that the participant is touching in this data, we can use this prompt to supervise our network. We call the type of data with the pressure sensor fully labeled and the data without weakly labeled. We can only collect a limited diversity of fully labeled data. However, since we don't have any restrictions when collecting weakly labeled data, we can collect a wide diversity. We formulate a weak contact label based on the prompt given to the participant. For example, in this image, the participant is prompted to press all fingers at a high force. The contact label is a list of 6 bits. The first 5 bits describe which fingers are in contact, and the last bit describes if the participant was prompted to apply a low force or a high force. The contact label is then used to supervise the network. We use a segmentation style network to produce a pressure estimate, which is supervised with ground truth pressure labels. We add a loss where the network attempts to estimate the contact label. We also use an adversarial domain discriminator to align the feature spaces between domains. The two losses have a great effect, and they improve performance significantly. We show some results of a network trained using weakly labeled data. PressureVision++ generalizes to a wide variety of surfaces, and it works under a variety of room illuminations. This shows progress towards the goal of training generalizable networks. We also demonstrate an application of our work to mixed reality. While there has been tremendous development in virtual and augmented reality, the input methods for these devices are generally lower bandwidth than the interfaces for laptops and smartphones. These mixed reality devices often use controllers or hand tracking as input and have participants interact with mid-air interfaces. However, mid-air interfaces have disadvantages. In these two studies, participants wearing virtual reality headsets interacted with an interface floating in mid-air and also with an interface on a real surface. Both of the studies find that participants are faster, more accurate, and report less exertion when interacting with real surfaces. Inspired by this, we use our system to turn any surface into a touchscreen for mixed reality. We have a participant wear a MetaQuest 2 headset, and we mount an RGB camera to observe the hands. Finally, a desktop PC runs our network and sends these results to the headset. We can build a variety of interfaces using this. This demo shows a simple Pong game. We also show a person drawing with their fingertip on a table. The drawing is pressure sensitive, so higher force results in thicker lines. Finally, we also build a text input method. We conducted a user study with 10 participants and evaluated them based on their typing speed and accuracy. Our pressure estimator was most reliable with index finger interactions, so we instructed participants to type this way. This is a limitation of our system. The Quest OS also includes a direct touch keyboard, which uses hand pose estimates to allow the user to press the keys of a mid-air keyboard. We used this keyboard as a baseline. When we compare the results of the two typing methods, we find that participants are significantly faster on our keyboard, and 9 out of 10 of them said that they preferred ours. Also, many of the participants also reported that they found our keyboard less tiring to use, and the tactile feedback of surface interaction helpful. To summarize, our core idea is to collect diverse data by having participants self-label during data collection. We successfully train a network that generalizes to diverse surfaces, and our method enables touch-sensitive interfaces for mixed reality. Thank you.